Hi everyone, so we are going to continue with modeling periodic behavior and we are going to focus on lesson 5 today. In lesson 5, we will work with cosines. Okay, here are the lesson objectives. We will redefine cosine to include all angles of rotation. We are going to use cosines to model a context. We will describe horizontal motion of the rider on the Ferris wheel, and we will work with cosine graphs. Okay, so this is the information that we had about Ferris wheel. Let's recall the facts. We know that the radius of the Ferris wheel was 25 feet, the center was 30 feet above the ground, and Ferris wheel completed one revolution counterclockwise every 20 seconds. In the last few lessons, we focused on the height of the rider, but in this lesson, we are going to focus on the horizontal shadow casted by the rider. Okay, so again, we have our Ferris wheel. We got our initial ray, our final ray. We know the angle is theta and the radius is r. So to find the length of the horizontal shadow that point B will cast, let's create a reference triangle. First of all, this is going to be the shadow that we are going to work with. So that is the length we are going to solve for. And to draw a reference right triangle, we just drew the altitude, so the point B is going to be xy, and we know that cosine of theta is adjacent over hypotenuse, so that gives us x over r, because r is the radius, which is the hypotenuse in this case, and from there we can say x is equal to r cosine theta. Now another thing about r is that, remember, it's the hypotenuse of your right triangle. So r is going to be the square root of x squared plus y squared. This will come in handy when we move on from using circles and reference triangles to work with trig functions. Okay, so let's continue working with the equation of the length of the shadow. So we have in terms of theta, so length of the shadow as a function of angle would be r cosine theta, where length of the shadow as a function of time would be r cosine 18t. Now remember where 18 came from. We had angular speed, which is b, of 360 degrees divided by period. That's the relationship between angular speed and period. Okay, and we know that this Ferris wheel had a period of 20 seconds. So when you do 360 divided by 20, you will end up with 18 as your angular speed. Okay, and it should be 18 degrees per second. So we know that every second, the Ferris wheel covers 18 degrees of the angle, right? And that's where 18 comes from. Okay, so we need to fill in this table. So please pause the video and use the equation that we just came up with. And at every second on this table, find the length of the shadow. So pause the video now, do your calculations, and then come back and play it. Okay, so I'm assuming that you are done. And for the first one, we know the angle is 18 degrees because every second the Ferris wheel covers 18 degrees. We just established that. And we know radius of that wheel is 25. So our x is going to be 25 cosine 18, and that gives us 23.8. For the second, we know that the angle is going to double up. So you will end up with cosine of 2 times 18, and the length of shadow will be 20.2. For 3 seconds, we will have cosine of 3 times 18, so 25 times that, and that will give you 14.7. For 4 seconds, we'll have 25 cosine 4 times 18, and the value will be 7.7. For 8 seconds, you will have 8 times 18, and now you'll end up with a negative value. And it's okay, because remember, now we are working with an angle that is in the second quadrant. For the second quadrant, we are working with negative values of x, right? So, of course, you will end up with a negative length for shadow. For 14 degrees, you'll end up with negative 7.7. And then as you continue with the rest of the angles, you'll end up with these values. Now what I want you to do is keep this table handy, because in the next step we are going to graph this. Okay, so let's do a scatter plot for the data that you had earlier, and pause the video. Please do your scatter plot. You can do it on paper, which will take longer. You can also use a software to do it, like Desmos or your graphing calculator or GeoGebra. So this is what your graph should look like, and it should be points that are all over the place and you don't really see a clear pattern here. Okay, so now that we have our scatter plot, remember the equation that we used. It was x equals r cosine 18t, right? X is a function of time. What if we also plotted this equation? So in the same software that you use to do this data, do this graph, also type in this equation and then graph it. And you should be able to see this. Now here is the thing, for some of you, if you tried it, you might not see this graph because you probably are working in radians. You have to make sure that you're working in degrees. So once you have changed your angle of measurement to degrees, you should be able to see this graph. And that is a perfect alignment for your scatter plot. And we have seen a graph that is very similar to this. It's a wave-like graph, right? And you have seen this in the previous lessons when we worked with sine. Okay, so graph of the length of the shadow versus time elapsed, and that's the graph we have. And we know that the shadow length will be maximum at 0 seconds, right? And it will be minimum at 10 seconds. Why 10 seconds? Because that is the time to complete half a cycle. Okay, remember 20 seconds was period, so 10 seconds, the Ferris wheel would have completed half a cycle, so it would have shifted from the rightmost location to the leftmost location. Okay, now remember this chart that we had earlier? So, angles for which your cosine is going to be positive is going to be from this quadrant, so the fourth quadrant and the first quadrant. But the values for negative will be second and third quadrant. And it makes sense because the x values are going to be positive in the first and the fourth quadrant, but they'll be negative in the second and third quadrant. Okay, now we are going to compare the graphs. So we already did a sine graph, right? And we have now done a cosine graph. So if you plotted on GeoGebra or whatever software you are using, if you plotted fx equals sine x and you plotted fx equals cosine x, you will see these two graphs. Okay, now take a moment and make some observations about this graph. Remember, instead of using theta, I'm just writing x, but we know x is angle, and in this case I'm working with degrees. So if you compare these two graphs, we know that they have the same range and domain. Okay, because the maximum value that sine can have is +1 and minimum is -1. The same thing is true for cosine. Maximum is +1 and minimum is -1. They also have the same shape. The shape is not stretched out or compressed. So what is the difference between these two graphs? If you notice that there is a shift. There's a shift from cosine to sine, or you can say there's a shift from sine to cosine, and it's a horizontal shift. And if you notice clearly, there is exactly a 90-degree shift. So here, so my sine graph was at 0 at this location. My cosine graph is 0 at this location, and that is exactly a 90-degree angle. So the shift is a 90-degree shift. And we are going to use this information later on when we start working again with identities. Okay, so please try to remember this. Okay, let's move on to graph transformations. Remember, we have done this in previous lessons. So we worked with this function, f of x equals 25 sine 18x plus 30. Okay, and if I have a new function, g of x equals -3 sine of 12x plus 6, what are going to be the transformations? Well, we know that 30 in our f of x function determined the height of the center of the Ferris wheel. And now we have the height as 6. So from 30 to 6, we know that we went down. So we went vertically down 24 points. So it's a vertical shift downwards. Okay. Then the next thing is it's a vertical shrink. So we went from 25 to 3, and that determined radius of the circle, right? Which tells you the range between your maximum and minimum. And we had 25 as our amplitude or radius in f of x equation, but now we are down to 3. So you know that the range is going to shrink. So that gives you your vertical shrink. Then we have a horizontal stretch. Our initial function f of x had 18 in the equation, right? 18x, and we know 18 gives us angular speed. But now our speed reduced to 12, which means it's going slower, which means it will take a longer time to complete a cycle. And if it takes a longer time to complete a cycle, then I know that my graph is going to stretch horizontally. And the last thing is due to the negative sign. Okay, your whole graph will get reflected over your x-axis. So this is what you will see. Your original graph is the red one, f of x is the red graph, and the new graph, g of x, is the purple one. So take a moment, make sure you understand the transformations here, and then move on to the next one. Okay, so now we're going to do more graph practice, but now we are not really using the idea of transformations. Okay, so we got the same equation, g of x equals -3 sine of 12x plus 6. And in this case, we are going to use the idea of midline, maximum, and minimum. Okay, so for the midline, remember, is the line, the horizontal line that cuts your graph in two halves, the two vertical halves. Okay, so to find that, you know the range of sine is -1 to +1. So the midline is going to happen at sine as 0. And sine will be 0 when your angle is 0, right? So sine will be 0 when x is 0. So when you plug in that value into this equation, you will end up with g of x being 6. So your first midline point is 0, 6. To find your next midline points, you're going to have to do a little more work. So now let's look at the value 12, because 12 determines the angular speed, right? And we know the relationship between period and angular speed is that angular speed equals 360 degrees divided by period, or you can say period equals 360 degrees divided by angular speed. And from there you get 30 as your period, which means the cycle repeats after 30 seconds. Okay. Now your maxima and minima is going to be your midline height, your y-coordinate of your midline, right? Which we have as 6, plus or minus your amplitude. So +3 or -3. Okay, so that gives you some ideas. And the last thing is the graph will move from midline to maximum or minimum position every quarter of a cycle, right? So we know that cycle repeats after 30 seconds, which means 30 divided by 4, 7.5 seconds. Your graph will shift from maxima to midline to minima to midline to maxima. So every 7.5 seconds, there's going to be a shift from maxima to midline, or midline to minima, or minima to midline, or midline to maxima. Okay, so then that should help you do the graph. Okay, now graphing this is not very easy. It's definitely very easy if you were using a calculator, but if you're doing this by hand, it requires a lot of work. But as you practice more, it will become easier and you will be able to do this faster. Okay, in the next slide, we are going to see a very similar equation. And now we have cosine instead of sine. If you have already done sine and you see the next question and the only change is cosine, you know all you have to do is a shift of 90 degrees, right? Or a shift of 1/4 of a cycle. So from your previous graph, all you're doing is shifting your graph by 1/4 of a cycle. Okay, and remember your cycle lasted for 30 seconds. Okay, so your shift is going to be for 7.5 seconds. Okay, and from there you can also get your midline maximum and minimum points. Now, in case you didn't have your sine graph to start with, then you would repeat the process that we followed in the previous slide, and you will do all your midline maximum and minimum points to graph this. And that is kind of it for lesson 5. So we covered a lot of cosine stuff in lesson 5. I didn't do the takeaways for this lesson because that's basically every single slide we covered. Okay, so remember lesson 1 through 4, we worked with sine. Lesson 5 was cosine, but everything that we kind of did prior to that, we then looked at it with the lens of cosine, through the lens of cosine. Okay, so I hope that this lesson made sense. Please go ahead, do practice problems from your lesson 5, and we will move on to lesson 6 next time.